In this video I'm going to create a false color image that consists of 8 colors that highlight the different zones within an image that have similar intensity. And then using that false color image I'm going to create spectra from the data set of images. So the first job in identifying pixels of a similar intensity is to eliminate some of the artifacts of the measurement process. And that's why I'm looking at, in this file, atomic concentration images. Now they're not strictly atomic concentration images. We can see simply by the fact that we have oxygen highlighted in different areas of this image that we do not have a uniform homogeneous material that we can genuinely calculate atomic concentrations from. So what do I mean by an atomic concentration image? Well, these images are calculated from a set of 3 images that represent oxygen, carbon and silicon, and when I normalize these images using an option on the image processing dialog window that is described as quantify images, the reality of performing this operation is that I am dividing each image by the total image that's calculated from all 3 of these narrow scan regions, and in doing so I have eliminated what you see here, which are striations representing instrumental artifacts. They're present in the oxygen and they're present in the carbon. Less obvious in the silicon, but nevertheless these are all striations, artifacts of the measurement which we do not wish. More importantly, the relative intensity, which you can see here in the oxygen, it's far more intense in terms of pixels at the bottom of the image than it is in the middle. Though these do represent oxygen-rich areas, the impression that you get from this image is that you've got more oxygen at the lower part of the image. When we look at the atomic concentration calculation, you can see that that's not true. So the normalization takes out instrumental artifacts. It also takes out variation in intensity and anything else that would cause the signal to have a bias in a different part of the image from another. Let's consider the silicon 2p. This again suggests that we have signal that is of similar intensity in different patches across the surface. And what I'd like to do is create a false color image that will highlight the different zones and allow me to pick out spectra from different zones based on the relative intensity of these zones. The way to do this is to mark across the color scale a range, which then is entered into the false color lookup table dialog window. So we've gone from 0 to 44, and I can specify the number of steps in the color as 8. I've got histogram equalization on. I'm going to use the bicolor scale. So when I press OK, the image is then colored so we have an equal number of pixels for each color across the entire field of view. I now wish to make this the false color mask that I will use to calculate spectra. But before I assign this as the mask, what I'm going to do is perform an operation that will change the color of spectra when they're drawn in the active tile after I've created spectra from these images. And I can achieve this by looking at the palette of colors for the spectra. And when I look at the palette of colors, you can see that it is very different from the colors that we see here. So that's not what I want to do, but there is an option that says set the spectra equal to the tile colors, and for images these are the tile colors, and we can see now that we've got a list of colors that match the colors that are displayed here. So I will accept that. I'll turn off the display spectra using the scale, that's these color scales, and when I say OK, I now have my tile set up so that when I create my mask it will appear with these colors. And there's the false color mask now. And these represent the colors that Spectra will appear once I overlay Spectra in the active tile. So this will cause a correlation between zones on the image and Spectra colors when I display them overlaid in the active tile. So I have a mask, and these data were processed from the image data set, which contains carbon, oxygen and silicon. So if I wish to look at, for example, the carbon spectra and how they relate to the intensities of the silicon, I can calculate the sum spectra using colors option and overlay in the active tile. Let's just increase the width of the line so it's clear the different colors, and we see now a color scale that has been formulated based on the colors that we used to classify the pixels from which these spectra were calculated.